All right, so we're making all alkenes throughout this chapter. So it's going to be important that we're able to talk about alkene structure and also understand what it looks like from an orbital perspective. So first off, this is an alkene. I built this right here, so we have a model of it, and bring that up to so you can see it better. But essentially, we have the double bond here. And what would that double bond look like in reality? Well, it is a CC sigma bond that's right between the two nuclei of the atoms, but then it also has the pi bond, which is the p orbitals, and that's what we have in your note packet. The pi bond is the red and blue component that's above and beyond, made up of those dumbbell p orbitals, and then the sigma bond is right in between, and that's a carbon sp2 orbital bonded to a carbon sp2 orbital. We're going to want to be able to draw that kind of thing though with a molecule as this. So in this, how it's drawn here, everything that is a line is neither a wedge nor a dash, so everything's in the plane. So if I took that out to you, this is what it would look like. We have everything in the plane of my hand, essentially. But we can't really see the p orbitals there because they're coming out at you, they're going into the plane. So to see the p orbitals, we would have to turn the molecule sideways. So how do we draw a double bond sideways? And you can see once we draw it sideways, we see that everything's in the plane just like it was when we had it in this orientation. Now it's just in a plane, but it's the different way. So essentially what we did is we took the molecule and we're turning it like that. And that's what we're going to do here with the board. So essentially we are reorienting the molecule, and the CC of that double bond is right there, and we have the p orbitals above and below, and that's where that double bond is made. That's the pi bond and then the sigma bond. When we did that, this CH3, if we turn the molecule like this CH3 is now coming out toward you, and the other CH3 is going away. So essentially we would want a wedge to one of the CH3s and a dash to the other CH3 that's going back. And we could do the same thing over here if we wanted to, but it would just be with the hydrogen. So essentially one hydrogen's coming out, the other one's going into the board. So hopefully you can kind of see how that structure looks a lot like how the molecule, there we go, looks that I've made. We have a CH3 coming toward the camera. We have a CH3 going away from the camera over here. We have the pi bond that is in the plane of the board, and then we have an H coming out and an H going back. So that's how we can draw one of these alkenes in the plane of the board, or if we turn it this way, we have to kind of draw out those orbitals. So that's what an alkene looks like. That's its geometry. And what we have to also remember is that because we have the pi bond that is above and below, we can't rotate this. It's stuck because we would have to we'd have to pull that piece off or that piece off to be able to rotate them. So they're locked. So essentially we can have a trans alkene or a cis alkene. So let me make that trans alkene, or the trans is fine. So if I rearrange the molecule, now we have the trans alkene, and I just said it, that's okay. But anyway, we have this alkene, and essentially we can't rotate around that bond, so this is not in equilibrium with this. These are two separate molecules because we're not able to rotate around that double bond. And as far as the alkene geometry, we use similar nomenclature that we use in describing cycloalkanes when we're talking about alkenes. So what what's the difference between this and this? What would you use to differentiate this molecule versus that molecule? All right, you've taken a minute to do that. You paused it. Now you came back. And yeah, this has both of the CH3s are wedges. So this is the cis dimethyl. You could have, cis dimethyl. This is the trans dimethyl. So cis is on the same side, both wedges, both coming out. Trans is across from each other. So we do the same thing with alkene geometry. This CH3 is on the opposite side of the alkene than that CH3. So we would call this the trans alkene. And we look at where the alkene is. This CH3 on this one is on the same side as this CH3. So this would be the cis alkene, as they are on the same sides. And again, why does it matter? With single bonds, it doesn't matter because we can just rotate around those single bonds. But with double bonds, there's no rotation because we would have to break that pi bond if we're trying to rotate the molecule around. Yeah, back in a minute. All right, we're back. So we're talking about these two alkenes right now, and essentially my question is, what is the relationship between the two of them? Are they the same molecule? Are they stereoisomers? Or are they constitutional isomers? So take a minute, maybe define what those things mean to you. Hopefully it's right up here in your brain because we just talked about a lot of that stuff in Chapter 5. But select the one that you think is correct and then come back. So now you're back. And the answer is that they're not the same molecule because we can't rotate around them. They're not constitutional isomers because technically they have the same connectivity. 1, 2, 3, 4. 1, 2, 3, 4. 2 is connected to the same stuff that 2 is connected to. So same goes for 3, 4, 1. Everything has the same connectivity. So how are these related? They're stereoisomers. Beyond them being stereoisomers, there are two types of stereoisomers. What are those types? Yes, you are correct. They are enantiomers and diastereomers. Are these diastereomers or are they enantiomers? Great. Yeah, they're not mirror images, right? So they're not enantiomers, they're diastereomers. So that's the relationship between these two. Next question is, which one would be more stable, the trans or the cis? So try to answer that for yourself. What do you think? Which one's going to be more stable? Yeah, the trans is more stable. And why was that? Hopefully you maybe wrote out your own explanation that you had in your head. But we also have these gaps to fill in. Blank are less stable because the two groups are blank together, causing blank. So maybe try and fill that in without me. And you did. And now you're back. The cis are less stable. We just said cis or trans. Trans is more stable, so cis is less stable. Cis are less stable because the two groups are close together. They're close together. So essentially, this CH3 is close to that CH3. They're in the same plane. We're thinking about our Newman projections. What kind of interactions is that going to cause? That's going to cause a steric interaction, having those two groups together clashing with one another. For that reason, the trans is more stable, the cis is less stable. Now we're going to look at the additional types of alkenes below. All right, so cis and trans, they were stereoisomers. What is the relationship between these two molecules? What is the relationship between these two molecules? This looks like a long bond. What are those relationships? So pause the video, decide for yourself, reason it out for yourself, and then come back. All right, great. You did that. First of all, are they the same molecule? Well, if they're the same molecule, they would have kind of the same name. We don't know exactly how to name alkenes yet, but we can assume kind of the same system, the IUPAC system, where we're going to take the longest carbon chain. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 5 carbons with both of these. we could do left to right or right to left. Usually we do the one that gives the lowest numbers to things. So we're going to number from right to left here, because if we were somehow going to tell where that alkene was, it's first on the 2 position. So we would do the same numbering down here. So at this point, we see we also have a methyl group. It's on the 3 position. So these look like they are not constitutional isomers. 1 is a CH3, 2 is an alkene that has an H on it, 3 is part of an alkene bonded to a CH3. And essentially what I'm sure a lot of you see so far is that if we took this molecule and just flipped it over, it's going to fit perfectly on this molecule. So these 2 molecules are the same molecule. They're A. So hopefully you were able to see that without any problem. What about these 2? So you've already done that one as well. We can do that numbering thing again. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the alkene is on the 2 spot in both of them. But what's different here? Well, the methyl group is on the 3 position here. It's on the 2 position there. So that means that these have a different connectivity. If we were naming these molecules, this one would be 3-methyl, this one would be 2-methyl. So these are different molecules. They're not A, they're not stereoisomers because they don't have the same connectivity. So they have to be C constitutional isomers. So it's kind of our structural analysis of alkenes, and we're going to move on to look at some of the reactions. So that's coming up.